The mnemonics of an assembly language are not that important. Actually, they're not even necessary. The whole purpose is to generate a pattern of bits, ones and zeros, but how you go about doing that is up to you. You can see the bit patterns of a program in an assembly language listing. This is a simple example. All it does is compare the values of a couple of integers and make certain the smallest one is first. This is a listing of the program as it came out of the assembler. You can get such a listing by specifying the L option and naming the list file. You can see lots of things in such a listing. For example, if you use the reserve instruction to set aside some workspace, the amount of space assigned to that label is listed here. This one is 4 because 4 bytes are to be assigned for each of these symbols. If the symbol had been for 2 double words instead of 1, this would have been an 8. This is, of course, the BSS section, so these values are not what is stored in memory. They are values stored in the object code and used by the system at load time to allocate memory. This is an example of the value stored in memory. It's the hex representation of the enter opcode. The 2 bytes following it are 60 for push AD and 9C for push FD. The first thing this program does is initialize the 2 values to be sorted. This is the hex value for the opcode for copying a 32-bit constant value into a memory location. Now look at this. Part of the instruction is inside square brackets. That means it's a relocatable value. In this example, the value is 0 offset from the top of the block of data. The actual value will be calculated depending on where the program is loaded into memory. This part of the instruction is the value 500 shown in hex. Now remember, with the Intel chip, numbers are stored in memory backwards, so the bytes are shown here the way they appear in memory. This is the first part and the second part of the 32-bit number. You have to reverse them to read what they are when they're loaded into a register or used in an expression. This is the number 200, also shown in hex in reverse order. And this is 4 offset into the data area with the offset shown in reverse order. In this program, before the numbers are sorted, they are displayed by being loaded into registers and having the registers dumped. And look at this. The address of the external function is shown as 0 inside parentheses. This is the assembler's way of showing an external reference. This value will be filled in by the linker when all the modules are hooked together, and that value will be adjusted again by the loader when the program is run. These 6 instructions are the heart of the program. The 2 values are compared, and if they're out of order, they are reversed. You can see here all the opcodes and the data references embedded inside them. In particular, you can see an example of a short jump instruction. It does not jump to an address, it jumps a number of bytes away from the current location. That way, the instruction is short and there is no relocation of an address necessary when the code is moved to a different location. But this same program can be written without using mnemonics for opcodes. It can be written by using pseudo-ops, creating bit patterns. For example, here is a declare double pseudo-op that creates a 32-bit enter instruction. Notice that the hex digits are written in reverse order that they appear in the actual object code. The assembler does it that way because when the Intel chip loads the value from disk, it reverses it. These 2 8-bit instructions are the 2 push instructions at the top of the function. This is the opcode for copying a 32-bit immediate value, a constant, into a memory location. And this is the memory location. It has to be declared by name so that when the module is relocated, the address referred to it is adjusted by the linker. Such a relocatable address is always shown in square brackets in the listing. This is the constant value, which is written in base 10 but converted to binary to be stored inside the instruction. It's shown listed here as a hex number. Coding it this way caused the necessity of one slight change to the program. The external function is called a little differently. It's called by having its address loaded into a register, and then the address is called. That was done because the assembler handles address resolutions differently in the call-up code. I'll have more about this later in the chapter on global offset table. Here is the main body of the function. It compares the two values and swaps them if necessary. As you can see, it is all coded as declaratives with hex values and symbol references. This is the way the first computers were programmed, by entering all the ones and zeros. When the first assemblers were devised and you could just type in names for the instructions, it was said that programming was automated. There would be no more need for programmers. Anybody could do it. They said the same thing again with the higher-level languages, Fortran and COBOL, and they're saying it again now with IDEs and drag and drop, but they're still wrong. The point to all this is so that you know there is nothing magic about the names, the mnemonics. They only exist to make it easy for you to remember what to type in to get the bit patterns that you want. You can make up your own mnemonics if you want. At the top of this example is a macro that produces the code to store a constant value. Don't worry about how macros work just yet. This macro is called STI, and it produces the 3 lines of opcodes shown here. In this version of the program, the macro is used twice. I called it STI because it stores an immediate 32-bit value into a memory location. Here the instruction is used to store the number 500 in the location called value 1. Now it does that by generating these 3 lines of code, so as you can see, you can make up any assembly language you'd like to use. A lot of people have done this, and they get very elaborate with the languages, and they call them compilers. The next lesson goes into some details about macros.